We explained in Calculate Moon Orbit, Real Physics, number 15, that the Moon is driven by the gravitational fields of the Earth and the Sun. However, there is another important factor in the origin of the Moon's orbit, inertia. So the lunar orbit was created by three forces. We first look at how each individual factor contributes to this. When the Moon orbits the Earth at its orbital velocity, its centrifugal force is as great as the Earth's gravitational pull. It runs on its round base circle, basic orbit. When the Moon is outside or inside the base circle, its speed is less than or greater than the orbital velocity and the Earth's gravity is greater or less than the centrifugal acceleration of the Moon. And is it attracted by the Earth or repelled to the outside? This creates a difference between the gravitation of the Earth and the centrifugal force of the Moon. So due to the influence of the Earth there is a tendency towards a circular orbit. Influence from the Sun. Because the Earth and Moon are driven by the Sun's gravitational field, the angular velocities of the Moon and Earth around the Sun are not always equal. This creates a difference between them. When the Moon is outside of the Earth's orbit around the Sun, the angular velocity of the Earth is greater than that of the Moon. In square 1, from point 1 to 3, the delta omega increases, and in square 2, from point 3 to 5, the delta omega decreases. These effects cause the y-axis to stretch. When the Moon is within the Earth's orbit around the Sun, the angular velocity of the Earth is smaller than that of the Moon. And in square 3, from point 5 to 7, the delta omega decreases, and in square 4, from point 7 to 1, the delta omega increases. These effects also cause the y-axis to be stretched down in length. So if it were solely the influence of the Sun, the lunar orbit would look like the outline of an American football. Although the elongated axis would always point to the Sun. Influence from inertia. When the Moon deviates from its orbit, this represents a superposition of two movements, one tangential and one radial. The effect of this tangential movement has no influence on the orbital deformation. The radial movement is responsible for changing the shape of the track. This also creates a radial inertial force that always counteracts the radial force. The radial motion is a reciprocating motion about the base circle, like a pendulum motion about a neutral point. In this, the Moon stays in its radial speed state due to its inertia, which is always opposed to the external force acting on it. Of course, the following principle also applies here: in order to be able to change the speed of a body, regardless of whether it is about accelerating or braking it, you need a force that is greater than inertia. To explain the whole lunar orbiting process, let's start from point 3, the farthest point where the radial velocity v theta is 0. Hence the inertial force is 0. At this point the delta g reaches its maximum. Although at this point the delta omega is bigger than 0, its effect in the radial direction is 0. According to point 3, the Moon is pushed inwards by these two driving forces, delta g and delta omega, resulting in a radial velocity v theta that always increases from 0. And against this, inertia is used, which increases with radial speed. It will come to that point, p4 about, where inertia will balance out driving forces and speed will be limited to maximum. After that, despite the driving forces, the speed cannot be accelerated any further, and the Moon runs undeterred in radial direction inwards with this speed, which is maintained by inertia. At point 5, the driving delta G and delta omega are reduced to 0. And the Moon can easily cross P5 or the base circle inwards. Below P5 the driving delta G and delta omega increase again, this time acting against the radial motion. Because they are initially smaller than inertia, the Moon's speed cannot be prevented except to the point, approximately P6, where it balances out inertia. After that, the speed is throttled and the inertia is also reduced, up to point 7, where the radial speed is reduced to 0, and with it the inertial force. The effect that the Moon moves far inwards below point 5 against the driving forces, delta G and delta omega, can be easily explained analogously to the pendulum movement, in which the pendulum can swing upwards against the Earth's gravitational pull. See video How does the pendulum movement work physically, Real Physics, number 5. On the same principle the Moon runs from P7 to P3 with reversed radial direction. This is how the lunar orbit came about. And inertia plays a very important role in the whole process. Without this, the question of why the lunar orbit is like this can never be answered concretely. In Calculate Moon Orbit, Real Physics, number 15, we took point 1 as the starting point. The Moon is pulled outwards by the influence of delta omega. After the Moon has gone around the Earth once and returned to its initial position at point 1, it now occupies a radial velocity that remains with the inertial force and easily traverses point 1, as it did at point 5, but outwards. Because the value of delta omega is initially smaller than the inertial force, the radial velocity cannot be influenced by it. As has been said many times, to change a body's velocity requires a force greater than the body's inertial force. As the Moon moves further outward, the force delta G increases to the point at which it balances itself with inertia. This point is also equal to the point at which delta omega and delta G initially balance out if the reciprocation is not dampened. Now the function delta omega created by the Sun no longer has any influence on the radial movement of the Moon, instead inertia takes over this function. Delta omega now only plays a role as a replenishment of energy. Of course, this is also necessary so that this process can go on forever. If the Sun's gravitational field now disappeared for the Moon, then the Moon's to and fro motion would have been due solely to mutual action between delta G and inertia. Just as a pendulum will come to rest, the Moon's back and forth movement will slowly cease until its orbit finally returns to its original circular path. The question of when and where the furthest point or closest point of the Moon has reached the Earth is not determined by the Sun's gravitational field, but by when and where the inertial force reaches its 0 point. This allows the perigee to constantly change. We have seen that the lunar orbit is a reciprocating motion about the base circle. If we clipped the lunar orbit and stretched the R0 circle to a straight line, it would have looked like the plot below. And this movement is on the same principle as that of a vibration. Therefore, this back and forth movement can be roughly described with an oscillation formula. The distance from the Moon to the Earth is equal to the sum of the radius of the base orbit and the excursion height of the oscillation. This is a simple lunar orbit formula based on real physics. The current position of the Moon's orbit can be determined with the phase angle phi. In order to distinguish it from the previous elliptical orbit, we call it the real orbit. Thank you very much for your attention. See you next time.